When we think about the future of technology, AI, national security, all of it, it's easy to picture these huge abstract ideas. But what if I told you a huge piece of it all comes down to one single machine, an unbelievably complex machine? Well, today, that's exactly what we're digging into, China's high-stakes race to build it.
So, is it happening? You see this question everywhere, right? It's really at the center of the entire global tech race. But to get a real answer, a meaningful one, we have to cut through the noise, ignore the headlines, and just look at the evidence. So what do we actually know? Let's start with a number. A big one. It kind of sets the stage for everything else.
$250 million. Just let that sink in for a second. $250 million. And get this, that's not for a whole factory. Nope, that's for one single machine. The one that makes the most advanced microchips on the planet. I mean, that price tag alone should tell you we are dealing with something on a completely different level of complexity.
Okay, so what in the world does this $250 million machine actually do? Well, it is the absolute heart of a process called photolithography. And honestly, without it, our entire digital world just wouldn't exist.
The easiest way to think about it is like a projector, but, a hyper-advanced, ridiculously precise one. Photolithography uses this incredibly focused light to basically print, or etch, these unbelievably complex patterns. We're talking billions of microscopic transistors onto a thin wafer of silicon. The more precise that light is, the smaller you can make the transistors and the more powerful the chip becomes. And that's where the real challenge begins.
All right, this is where we get into the nitty-gritty. For years, the standard was something called DUV, or deep ultraviolet. It works great, but for the kind of chips that power today's most advanced AI, you need a massive leap in precision. You need EUV, extreme ultraviolet. And here's the kicker, the really big deal. According to our sources, there is only one company on Earth that makes these EUV machines, just one, ASML, based in the Netherlands.
So that leads to the obvious question, right? If ASML is the only one, why doesn't somebody just buy one, take it apart, and copy it? Well, the answer is pretty fascinating. It's because ASML doesn't really just build a machine. What they do is orchestrate this massive, global web that took decades, literally decades, to create.
Yeah, this quote just nails it. An EUV machine isn't some single invention you can just reverse engineer. It's more like the final product of a global super team. The absolute best minds and best companies from all over the world, each contributing their unique piece of the puzzle over a very, very long time.
And this just drives the point home. I mean, look at this global puzzle. You've got world-leading specialists for the mirrors and lenses in Germany. The unique light source technology, that comes from the US. Then you have a web of literally thousands of other suppliers providing everything from specialized chemicals to robotics. ASML's real magic, their secret sauce, isn't just one component. It's integrating all of these pieces into one perfectly functioning system.
So, knowing all that, how insanely, mind-bogglingly difficult this is, why is China pouring so much effort into trying to crack it? Well, the answer is actually pretty straightforward. It all comes down to national self-sufficiency and the ambition to lead the next technological revolution. And this right here is the whole ballgame. Because let's be real, the country that masters making the most powerful chips will have a massive, massive lead in the race for advanced AI. We're not just talking about faster phones here. We are talking about the engine that is going to drive the future of medicine, finance, and national security.
Which brings us to the key question, doesn't it? What is the actual evidence of progress? This is where we have to be really careful. The ambition is crystal clear. But what do the sources actually confirm about what's happening on the ground? It is notoriously difficult to get a clear picture.
So let's look at this state of play, ambition versus what's actually confirmed in reality. The goal? A homegrown, in-house EUV machine. The reality? According to our sources, for now, ASML's the only game in town. The application? Advanced AI chips. That is confirmed to be a top national priority. And the investment? We don't have hard numbers, but when a single machine costs $250 million, you can bet the national focus is intense.
All right, to really get why there's this gap between ambition and reality, we need to look at the specific monumental hurdles involved. Let's talk about the real bottlenecks. There are at least 3 immense challenges here. First, the light source. To even create EUV light, you have to blast tiny droplets of molten tin with a high-powered laser twice. It's an incredibly violent and complex physics problem. Second, the optics.
EUV light is absorbed by almost everything, so you need the smoothest mirrors ever created by humanity to guide it. A true materials science miracle. And third, system integration, getting tens of thousands of these hyper-specialized parts to work together in a vacuum with perfect precision 24/7. It's just staggering. So, given these massive challenges, what happens next? Nobody has a crystal ball, so instead of making one single prediction, let's explore three possible futures, three scenarios of what we should be watching for.
We can really see three potential paths. First, there's slow but steady progress, always staying maybe 2 or 3 generations behind the cutting edge. A second, and very plausible route, is mastering the older DUV technology with incredibly clever engineering to stay competitive. And the third is the long shot, a genuine EUV-level breakthrough, a major leap that would completely redraw the tech map.
And this is the key takeaway for anyone following this story. A so-called breakthrough might not look like a perfect ASML clone. It could be an entirely different approach to solving the same problem. The details here are absolutely everything.
So as we wrap up, let's boil it all down. Here are the three things to remember from this explainer. 1. That $250 million EUV machine from ASML is, for now, the only game in town for the most powerful chips. Period. 2. Copying it isn't just hard. It requires solving fundamental physics problems and replicating an entire global supply chain. And 3. This is not an academic exercise. The quest to master this technology is directly tied to the future of AI.
And that leaves us with a much bigger question, doesn't it? So much of our modern world is built on global collaboration. But what happens when countries decide they need to go it alone on the most critical technologies? The answer to that question might just be revealed in the story of the chip machine. Thanks for joining us.